stay longer?
Yeah, just let the phone go.
Okay, then. It's tough, right? Kind of early today. But I see you are strong. You came in a massive group, which I was not really expecting. But, you know, we are in early days and, you know, the enthusiasm is still very much active. Now, we are talking about the problems which are precluding the fast execution of programs, assuming that I have a processor which is, let's say, richer than a normal processor. Then if I have hardware, right, I have transistors which are enough. As I mentioned before, today transistors are commodity. It used to be that we were supposed to save each and every transistor and each and every byte of memory. Now we don't really care for that. We care for the picowatts or milliwatts or megawatts, depending what kind of application we have. Now, our enemies are the hazards or the dependencies. And I would say this room is even worse than room B. There are essentially three types of issues. There are the structural hazards, which there is not that much we can do except to invest more hardware. Then those are things which are precluding the execution because I don't have enough functional units. Let's say I need an adder and all the adders are busy, taken. Those, not that much that I can do. There are the data dependencies, the data hazards, which very much depend on the application. The nature of the application may exhibit more dependencies or less dependencies. And in here we have three types of dependencies. Real dependencies, when I have a consumer-producer kind of relationship, then there is a relation between an instruction which is calculating something and another one which is using that result. And for those, there is not that much that we can do in the sense that there is no way to really cut them. And there are artifacts. And the artifacts are not real dependencies, but they look like dependencies. Then, when two instructions are writing in the same target, if I'm not following the order, I may create problems. But this is not real a dependency. I can solve that. Or when an instruction has to read a value and then another instruction has to write in that location, it's again a kind of not real dependency. Because I can read in that location and I can write in another location. But I should be careful to use the, let's say, the values in a proper way. Then, these like write after write and write after read are okay, and we can deal with them, assuming that we have resources and we have a mechanism to do that. And you will see in a sec the mechanism. And then we have also the control hazards, which again depend on the program. If we have no branches in a program, then there are no control hazards. Then we know we have only one line in the execution, and we can go like a train. No stops, no, you know, it's like a TGV, like a fast train, or a Shinkansen. I don't know how you call it in Chinese, probably also Shinkansen. Hmm? No? How do you call in Chinese the fast train? Because in China they have a lot of fast trains recently. They developed a very big network of what we call in Europe TGV or ICE, depending on who the provider is. I think there is also an Italian one. Not to offend the Italians if there are any. Okay, now, The idea is to do something in such a way that I can execute instructions even though the current instruction is stalled. That in a normal processor, when I'm taking one instruction at a time, if I can execute it, it's fine, I'll push it in the pipeline. If I cannot, I'll stop. What is happening in this kind of dynamic scheduling is that I'm not stopping, I'm looking for another instruction which could be a candidate for execution. Then I'm kind of doing look ahead. See, no good, no good, no good. Okay, you can execute. Go and do it. Now, let's say it's easy said and not that simple to done, because there are a lot of things which do happen around that. But it's a bit like on a highway, you know, you have a couple of lanes, and if you have a slow car, it will stay on the right and the others can pass. Now, it's not that simple as on the highway, but the principle is kind of the same. Okay, now we have here an example, and you see that we have a dependency between the first two instructions, and they are, you know, in my execution window. And the third instruction actually can be executed without having any kind of problem or content with the previous instructions. I don't think that's a good position. You will look like that. This is not a very nice cinema. Hmm? Okay, now. Bon. Then, this can happen in any kind of, let me move here. It's not very nice for you because you have to stay like that, but it's also for me, I want to see what's on the slides, not to deviate too much from the story. Now, we'll discuss dynamic scheduling in the context of a 5-stage pipeline. You can do that in any kind of pipeline. It's just an example. Now, in that kind of pipeline, before doing anything, you have to decode the instruction. Then ID, it's instruction decode stage. When you get an instruction, you decode it, and you do a couple of things. You check the structural and the data hazards. Structural hazards means if I have resources to execute it, and data hazards is related to the fact that I have the operands available and I can do the execution. And when the instruction is hazard-free, I can issue it to execution. Now, this is the standard way. In the out-of-order execution, which is this dynamic scheduling that we are talking, things are slightly different. Then we do the same story on instruction decode and structural hazard check, but on the data hazards, we allow for exceptions. And in which sense we allow for exception? We have to do something about the current instruction which may have a problem in such a way that eventually I can execute it, but I will not stop. I'll do something about that, and you will see what Tomasulo proposed to do it. He was a very smart guy, I would say. He proposed a very simple way to deal with a kind of complicated problem. And then I'm preparing that instruction which I cannot execute, and I'll put it somewhere, and I will go to the next one. And I will go to the next one. And I will keep on scanning the instruction, and I execute whatever I can. What I cannot execute, I will put somewhere in what we call reservation stations, or today it's slightly different, but I will save it somewhere, and I will let it execute whenever is possible. Then in this way, I'm not stopping, I'm not leaving behind instructions which are not executed, and I'm also doing things in such a way that I'm not damaging the results. then I'm still doing correct execution. Now, that kind of thing has data dependencies, which are real data dependencies, which I just said how we solve, but we also have to deal with that kind of artifacts. And that kind of artifacts can be done by what we call register renaming. Then if two instructions are writing in the same target, but there is no logical connection between those, let's say, registers in the view of the program, I can rename. Let's say I'm writing in both instructions in F0. Now, I may have another register which is available, and of the first one I'll use F0, and on the second one I'll use Fn. And further, after the execution of this instruction, Fn will be my F0 further, if this is possible. But if this would have been possible, the compiler would have tried to solve it. Or I can use something like not really architectural visible registers. Then you as a programmer, you see the instruction set, and you know that there are a couple of registers which are available from R0 to Rn. Those are architecturally visible instructions. You see them as a user. But you can make some registers which are not visible to you, but they are visible to this mechanism which is doing the scheduling. Then if I have twice F0, I'll use first F0. The second time I will use one of those not visible registers, and from that moment further, I'm taking care that things are not messed up. Now, this solves that kind of not real dependencies, the artifacts. Then essentially speaking, I have a very nice and clean way to deal with this dynamic scheduling. I'm executing as much as I can, depending on the amount of resources that I have, and depend on the instruction parallelism that I can find in my application. And there is one issue at the end. You know, there is always a price. If you make an investment, you get back a complication, you get back some advantages, and this is the out of order completion. You know, triple O means out of order. And if you do out of order execution, you can do in order completion or out of order completion. If you do in order completion, you have to have enough resources in order to memorize the instructions which you execute, and you will complete them. Then you will update the status of the processor in order. This will slow down a bit the process, because you may get a moment when this buffer is full. But you can also do out of order if you don't damage the status of the processor. Then you don't damage data. You don't damage the control flow. Now, depending on how you go, you may have precise or imprecise interrupts. If you care for precise interrupts, you have to do it in order. We discussed about precise and imprecise interrupts last time. Then essentially you refer to the fact that whenever you have an exception, your status of the processor, it's exactly the one that would have been when sequential execution would have taken place. In imprecise interrupts, you would have been around. Some of the flags might be changed because you executed other instructions. Okay. Now, here we have an example of register renaming. You see that there are kind of dependencies between the second and the fourth instruction, and the fifth instruction, and the second and the fourth instruction. But those are not real dependencies, because there is no consumer-producer relation. That's the real dependency. And how I can do that? I can do it very simple. You see, F6, I will use it as F6 on the last instruction, and on On the second instruction, I'll give it a different name. And it's called S in this example. It's S because, as I said, it's most likely not an architecturally visible register. It's still a register in my processor, but it's not one that you can use when you write an instruction. It's a register which is visible to this hardware mechanism, which is saying, you know, instead of using F6, you'll use this register. And this is the internal business of the processor. It's not visible to you or to somebody else. Now, the same story, I can do it with F8. You know, in the fourth and the fifth instruction, I'm using F8 as being T. And after the last one, I have to be careful that all the F8 which are appearing in the code should be actually T, because that's the one which holds the most recent copy of F8. Okay? Now, I have to be able to do that on the fly, somehow. It looks like a complicated process. But you will see that Tomasulo came with a very nice idea. Now, register renaming can be done by the compiler. And as I said, the compiler will try always to solve that kind of things. But the compiler is confined due to the number of available registers. Those, let's say, not really virtual because they are real, but they are not visible registers, are not visible to the user. By user, I also mean compiler. Remember when we were talking about an architecture, and I said it's a behavioral description of a processor as seen by a user. And the user is you when you write in assembly code, but also the compiler, which is transforming your C code in assembly. Then compiler has some kind of limited possibilities. Now, in hardware, if I have enough of those registers, I can do a better job, and it's more than that, I have the view on the dynamic situation. What is happening in practice, it's exactly what I see. The compiler can only see static. That is not data dependent. I don't really see that kind of things. Now, it's always a price to pay. If I do it in hardware, it will cost me area, but I don't care, but it will cost me energy on my application. If I do it by compiler, there is no area overhead, or it's less area overhead, and it will cost me zero energy at execution. I'll spend energy at the compilation, but essentially when I have compiled, I'm connected to the power supply from the wall. And we assume that there we have enough energy. That used to be the assumption. Today, with this kind of data centers, things are getting a bit more complicated. Okay. Now, Tomasulo came with an idea which was doing register renaming, let's say, by construction, in an implicit way. And, come on. Okay. And he came with a proposal, and he kind of decoupled two processes. The instruction decode and the instruction execution are two loops which are going on in the hardware, but they are decoupled. And on, let's say, on the fly, in this process, he is also solving the artifacts, the not true dependencies. And he came with this kind of organization. You know, this can be variations about, and here we just concentrate on the floating point. It's an example, but this holds true for integer also. It's very early, right? You're sleepy. I envy you. Because I have to be awake, right? Long time ago, I was also sleeping in classes. But you know, I was doing something even better. I was not coming. You know, in my time, the presence was mandatory. We had a book of presence, and there were some professors which were really nasty, and they were calling the catalog. And okay, but that's a long time ago. Let's concentrate on Tomasulo. Then Tomasulo said the following: I have a processor, and for that processor, I have a certain structure where I have more than one functional unit per type. And what you see here is that I have a couple of floating point adders and a couple of floating point multipliers. This allows me to execute more addition and more multiplications in parallel because I have enough resources. Now the question is how to feed those functional units in parallel with as many instructions as I can, assuming, you know, the dependencies in the program, and also solve the other issues like, you know, not real dependencies. And he said, you know, why am I stalling? I'm stalling because I have an instruction which has one or two operands which are not available. That's one reason to stall. Now, if I'm decoding such an instruction and I see that one of the operands is not available, I have two options: to stall or to save it somewhere. And he said, okay, I know that the type of the instruction. If I put a buffer behind the functional unit, I can stall that instruction, I can store that instruction in that buffer. And then he came with the concept of reservation stations, which means that behind of the functional units, he put some buffers, and they are called reservation stations. You see, I have reservation stations for adders and for multipliers. 3 for the adders and 2 for the multipliers. Now, whenever I have an instruction, I'll decode it, and I will put it in the reservation station of the functional unit which may execute it. Then if I'm doing an addition, I'll put it in the reservation station of the adder. If I have multiplication, I put it on the multiplier. Then somehow, if the instruction is ready for execution, it's like before. You put it there, the functional unit will take it, will execute it, and that's nice and clean. If the instruction is not ready for execution, the instruction is still in the reservation station, and some other process will take care to update that reservation station whenever the missing operands will become available. Then, if I look from the instruction decode, fetch and decode point of view, I can look at instructions and say, okay, addition. 1, 2 operands, okay, this is missing, no problem. I'll put a tag here and I'll put it in the reservation station. Multiplication, I'll put it there. Then I will never stop in looking at the instructions except when all the reservation stations are full. That's one part of the loop. The other part of the loop is to solve those issues which I postponed. Then I said, you see, okay. Then I put here an instruction which was missing an operand. I don't know the value of that operand. Eventually, those functional units will execute and will produce that result. What I have to do now is I have to take the result. Let's say the result is coming from here. It's an operand which will take part of an addition here. I have to be sure that that result will be updated. Then when the multiplier will put the result here, I'll have to be able to say, that's the result that I'm looking for. Then I will memorize it here where was missing, and now my instruction is ready for execution. Then you see, in this way, I'll go on the details. I'm just trying to explain you the concept. We'll go in, we have a couple of slides on that. This is a very important concept, and in my view, in the book, it's presented with examples, and it's not really, explained in a more philosophical way. Then, somehow, in this reservation station, I have to know that a value which was put for output by the multiplier is the one that I'm looking for. Then I have to memorize in the reservation station somehow something which will allow me to say, okay, this is the result that I'm looking for, or no, that's not the result that I'm looking for. Now, how are those things going? When functional units are executing and they have a result ready, what they do is they put the result on this bus. This is a common bus. Then I put the result here, and whoever needs it will take it. But now, in order to do that, I have to put the value, but also a kind of signature of the result. What is this result? And let's say I am executing an instruction where this result has to update a certain register. Then it will be loaded in the register whenever a register here knows that the result of this reservation station should be stored there. But in the same time, other reservation stations will see that's a result for me, and I will update an operand. Then, just disregarding the details, I have now two loops, two decoupled loops. The instruction fetch and decode, which will process instructions one after the other, will store them in reservation stations, regardless of the fact that they are ready for execution or not. If they are ready for execution, they will be stored with the values from the registers which are the input of that instruction. If they are not ready for execution, they will be stored together with some information about where to get the value from. And that's a tag of a reservation station which will produce that result. Then, except when I have all the reservation stations full, I will never stop. That's first loop. The second loop will be the execution. Now I'm executing, then a functional unit, will execute whenever a reservation station has an instruction ready for execution. Instruction ready for execution means instruction with operands value available. And all the functional units can execute in parallel. After the execution, the functional units will put results on the bus. Now, I cannot put all the results in the same time on the bus. There is a certain pipelining going on, because this bus, it's one, common structure, and one functional unit can talk at a time. On a bus, there is only somebody talking at a time. Otherwise, we get, cacophony, if you know a bit about music. Let's say interference on the bus. If we talk in parallel, nobody understands what we are talking. It's the same story. Now, when I'm putting the result on the bus, I'm saying, this is the result coming from reservation station I, and this is the value. Whoever needs it, should take it. Then other reservation stations can Look on the bus. You see, the bus is going in this to the function, to the registers, to other reservation station, to this load store unit. Then other reservation stations which are waiting for that result will recognize it and will say, ah, that's for me, take it. The register file can do the same. And in this way, now I am executing, producing results, and unlocking instructions which are in the reservation station and were not ready for execution when they were decoded, but now they can go. And in this way, by decoupling these two processes, we solved the problem of stalling. Then the stall will occur only when not enough resources are available. Now, the number of reservation stations will depend on what I want to achieve, what my budget is. But as a principle, there is probably an optimum amount of reservation stations which will make sense. Because remember, we have branches. And somehow, before solving a branch, there are no instructions that I can process. Now, if I can do some kind of prediction on branches and do speculative execution, then it makes sense to have more reservation stations, because I'll have more instructions to process. If I'm not doing that, there is no need for that. So far, so good. Have questions? No, brilliant.
I have a question. So, just to make sure I'm on the right track, with the Thomas-Sewell algorithm, we're avoiding all types of hazards?
Data hazards.
Data hazards.
Data hazards.
Okay.
Not control hazards. And structural hazards, it's again, we cannot deal with them because they come from the resources. If there are not enough resources, tough luck.
So only data dependency.
Data dependency we solve in a very clean way. Now, let us look a bit on details. Because I explained you the general concept, I think it's important to understand the concept and then you can look in the details. Okay. There are different approaches in here. There are people which are looking in details, presenting the pieces, and then talking about the big picture. I prefer to go the other way around. It's a matter of taste. Right? Which one do you prefer? None.
None.
You don't care. You just want a grade for the course. Okay. Brilliant. That's, you know, a typical cost-effective attitude. Okay, now we are talking about reservation stations. As you see, in a normal instruction, I have the opcode and then I have the operands. In a reservation station, what I have, it's somehow different. I have the opcode because the functional unit can execute more than one instruction. Then I still have to tell the functional unit what to do. I'm doing addition or subtraction, or I may have a multiply and accumulate functional unit which can do only multiply or multiply and accumulate. And you know, the ALU can do also logical operations and things like that. If I would have issued to an ALU, I would have said operand, opcode, operand A, operand B, value-wise. Now, because I may not know the value of the operands, what I'm doing is I'm saying, if needed, instead of the value of the operand, I'm saying, you know, the reservation station producing operand 1. I know that there is a dependency and my operand 1 will come from a previous instruction. On that previous instruction, I put a tag on the register, which is the output of that instruction, that output will come from reservation station 10. Now, when I'm looking at my current instruction, I'm saying one operand is available, the other one is said in the register file is not available, but it will come from reservation station 10. Then instead of writing in my register, in my reservation station the value, I will write, this will eventually come from reservation station 10. And that will be a code, a tag, some bits. Depending on how many reservation stations I will have, it will be the logarithm of the number of stations in bits in order to allow the combinations. Now, then, when I place the instruction in the reservation station, I have to fill in those fields, whatever I can fill. But I can always fill something, value or reservation station. That's from the point of the input. Now, from the point of the output, I have to say where the output of this instruction will go. You know, because when the functional unit will take that instruction from the reservation station and will produce the result, the functional unit should broadcast the result together with the signature of the result. Then I have a result, it's 20. And I'll put it on that common bus. But I have also to say this 20 belongs to reservation station 10. Whoever is waiting a result from reservation station 10, that's your result. Which means that you will have to put here in the registers, you have to fill in a tag and say, you know, this value in here, it's actually not valid. This value is waiting for a result from reservation station 3, and whenever that will come, the value will be valid. Then I will clear this field, and I'll put the value. This will update my registers, my architected registers in a proper way, but also by broadcasting this reservation station 3, all other reservation stations will know that the value is available, and they will say, okay, I was waiting here for a result from reservation station 3. Okay, it's now on the common bus, I'll store it here. Because I have here and here values, then this reservation station now has an instruction ready for execution, and I will pass it for execution. Okay. Somehow I explained you that, but I will go once again because, you know, this is a very important concept and you like to hear it. Yes?
Well, what happens if there's, say, a write, then a read, and then a write on the same register? Because first it's waiting on the first write, then the read can happen, but then somehow it still has to detect that it's now waiting on the second write. That's also in the reservation buffer.
Then it's a what you took it me too fast. It's a
Write,
write,
then a read,
okay.
and then a write on the same register.
Then I do renaming because that register, or there are two issues. If I can do renaming, it will be no problem. If I cannot do renaming, I have a structural hazard and I have to wait. Because that instruction will go in a different reservation station. Then it comes, if I can do it, I'll fix it. If there is a structural hazard that I don't have enough reservation station, I have to wait. Now, when I'm executing, as I said, I'm broadcasting to everybody who wants to listen to me the result plus the identification of the result. And as you see, it's going to all the other reservation stations and it's going to the registers. And it may go also to the load store part, which is not here. Then, when both values are available, I can execute. Now, if all my functional units are busy, I cannot execute. Let's say I may have 3 reservation stations ready for addition and 2 headers. I cannot execute 3 additions in the same time if I only have 2 headers. But things, will go okay. Okay. Now, part of the execution of a program, we also have the load store, right? I mean, we have the part which makes sense and is doing useful computation, and we have the part which is feeding the functional units with data. And if I have a load store instruction, I am dealing with the situation slightly different. If we talk about a load, then if my current instruction is now a load, what I'll do is I will pass that instruction to the address unit, which will compute the address in the memory, and then I'll place the load in the load buffer. And that will be executed whenever the memory is available and things will work as before. Then I see the load buffer a bit like a reservation station in the sense that it's a queue, but there is no mechanism of doing kind of implicit addressing and calculation. Then whenever the load is executed, we'll update the register which is the target. Now for the store, it's kind of the same, except that when I'm doing a store, I'm taking a value from a register. If that register is a valid one, which has a valid value, the store is ready for execution. And it will go in the store buffer, address, and value. If that register is not holding a valid value, I'll do the same trick. Instead of writing the value, I will write the name of the reservation station which is producing that result. And whenever the functional unit will provide that result, that will come now via the common bus back in here. And in order to have, things under control, load and stores are executed in order. And in here, we process them in order. Okay, break. You look tired, then you deserve a break.